Okay, let's start again. So these are the two last lectures. Sanjib told me that I can talk without stopping till 9 o'clock this evening. So, and in fact we need it because I'm roughly at 30% of what I prepared. So I need almost twice the time that I already took, including the tutorials. So I will try to emphasize some similarities with what Satya told us today. So this will be, I think, a nice wrapping of all the subjects. Just to remind you, at least 2 days ago, we were in the middle of a calculation. We were interested in the total displacement, total current of all the particles in the asymmetric exclusion process on a ring. A priori, this problem has nothing to do with what Satya has been teaching you during this last week. In fact, the problem is very closely related. And we want to compute a large deviation function for this total displacement, total current, time and space integrated current. I compute with positive and negative signs all the jumps of all the particles through all the bonds. Okay, if I were sitting at only one bond, I would be computing the current through one bond, and now I'm really computing it everywhere. Okay, so the object which is important is a large deviation function. I spent a lot of time trying to argue that large deviations are the right mathematical object that could generalize potentials, thermodynamic potentials in many different processes, including far from equilibrium. Then technically we saw that knowing the probability distribution or knowing the cumulant generating function is the same thing up to a Legendre transform. Then, and again Satya emphasized that we saw that this cumulant generating function, E of mu, can be realized as a maximal eigenvalue of a deformed Markov matrix. So not a deformed Hamiltonian. In the case of Satya, it was a deformation of the potential, therefore of the Hamiltonian. Here there is no Hamiltonian, it's a Markov process. But what plays the role of the Hamiltonian is the Markov matrix. So maximum eigenvalue of a deformed Markov matrix, Markov operator, Markov generator, Markov matrix. All these words are the same. That I call M of mu. And the deformation in that special case, but you change the problem, you change the deformation, is just adding a fugacity for positive and negative jumps. And fugacity comes as exponential mu and exponential minus mu. I think we did the calculation quite explicitly last time. Okay? So you see again a maximal eigenvalue to investigate. Of course, M of mu is not at all a random matrix here. Not at all. It's really the jumps. It's totally deterministic. It's full of zeros. Okay? But okay, it's you know, the frame is very similar, and the methods are very different. The miracle is that M of mu, although it's not a Markov process anymore because the columns do not sum to 0, it is still an integrable process, integrable in the sense of Bethe Ansatz. So I'm going to spend the next 9 hours to rederive the Bethe equations. No, I'm not. I'm not. But maybe I will spend, I intended to spend 0 seconds. Maybe I'll spend 60 seconds to tell you again. So now we have to solve this type of equation, d of, it was ft, I think I remember yesterday, ft of mu and c, dt is m of mu ft. okay, so on. Remember, so we want to diagonalize this matrix, so we want to find psi's such that it's E psi. And if we write explicitly this equation, what is this equation going to be equal? Again, a configuration is given by a position of the particles, and I write only the generic equation. So because of this, P, which is the forward jump, and Q, which is the backward jump, P will be changed into P exponential mu, and I can enter by x1, xi minus 1, xi, xn. Q will get an exponential minus mu, and I can enter from xi plus 1. This is a generic equation, and beware, the diagonal terms do not get, I don't want to use the word renormalized, I mean it's not renormalization, do not get changed or do not get, yeah. I mean now physicists use the word renormalized even when they go from, you know, francs to euros or rupees to francs. I mean, money is renormalized. We should not exaggerate with that. Renormalization is serious. Okay, so beware, it's not exactly the same equation. This is the generic equation. There will be collision terms when two particles are next to each other. Again, there can be 3-body, 4-body collisions, but I told you it's integrable. So there will be only 2 collisions, which are important, 2-body collisions. I'm not going to write the equation. You have to modify it yourself. Put the exponential mu's where they are and don't put them where they are not. The 2-body collisions, starting by a Bethe Ansatz trial function, which is the sum of our permutations of A sigma, Z sigma 1 x1, Z sigma n xn. Again, putting them into the equations, keeping the exponents fixed and the z's fixed, and comparing terms which are alike. So again, it looks horrible when we did it in the lecture. Maybe it looked even worse when I did it yesterday. But if you do it once or twice, you see it's, in fact, it's extremely simple. In my notes, it takes half a page. So, and I write quite big because my eyesight is becoming weaker, so I write bigger and bigger. So it's not tiny, tiny. But you just have to see, look at the things and just compare things which are equal, which have to match. So 2-body collisions will allow you to compare, to find all the ratios of amplitudes which differ by a switch, okay, by exchanging I and I plus 1. These ratios, again to use words, but sometimes fancy words have a kind of poetic appeal. So this is called scattering. So in fact, the image is not too bad. You have the particle I and the particle I plus 1 which collide, okay. So all the other ones are spectators. Zi plus 1 or xi plus 1 collide, and they scatter, and they reflect back, and there is a scattering amplitude of this 2-body process. It will be the same. The scattering amplitude will be given by the ratio of 2 polynomials of degree 2, like this P, Zi, I don't remember, plus Q, Zi plus 1 divided by blah, blah, blah. Okay, I will give you the answer because we'll need the equations. And the beautiful thing is that 3-body collisions can factorize into 2 bodies. So if 3 guys are colliding, you have just to consider pairs and not direct 3-body, so they factorize. So this will fix all the amplitudes, the 3-body collision conditions. The scattering of 2 bodies will fix all amplitudes up to our overall factor. All amplitudes are fixed. And then you have the periodicity condition. The periodicity condition compare the configuration with the configuration obtained by circular permutation, because the last particle becomes the first. And this gives you some ratios. So this will give you the ratios of the type A, n, 1, 2, 3, n minus 1 over A, 1, 2, 3, n, circular permutation. And this will tell you that this is something like Z, I remember, Z1 or Zn to the power L, and so on, all circular permutations. So these periodicity conditions, in fact, I already told you that these guys are all determined in terms of the Z's. So because of these two collisions, all A's are known as functions of Z's. They are all known. So these periodicity conditions will give you equations in Z's. In other words, they will quantify the Z's. They will tell you that the Z's are solution of some polynomial equations. So this is the periodicity which quantifies the Bethe roots. So at least the image is quite simple. You see, integrability is that two-body collisions are enough. The scattering matrix of three body is a product of the scattering of two bodies, of four bodies. It's a product of two bodies. So you don't need to consider multiple interactions. Only 2 by 2 interactions are enough. These collision conditions fix all the amplitudes. And the periodicity quantifies the wave vectors. Just as in simple one body on a ring that you study when you do solid state physics, you know that the amplitude has to be 2k pi over L. Or when you put particles, independent particles, in a box, you have quantification of the modes. So here the quantification is highly nonlinear and complicated, but it's the same type of quantification. If we are in an infinite system, which will be the case by the end of the lecture today or tonight, if we are in an infinite system, there is no periodicity, so no quantification of the wave numbers. But of course, all scattering amplitude will be fixed. And again, if you want to learn this technique, if you absolutely want to learn it, the only way is, I think that's the third time I repeat the procedure, the only way is to do it once by yourself. So yesterday some people asked me for some references. I tried to look for some, and very bizarrely, I mean you can guess why, usually people in the notes or in even books and so on do the two-body case and then just say the general case is given by this. So there are some notes by which I find quite clear, but I'm afraid that he doesn't do the full calculation. Oh, I wrote the name in my notebook. You can close your eyes, your ears, because it's going to boom. So Fabio Franchini. I didn't use that at all because I didn't know about it. Somebody told me about it a week ago before I came, so it was a bit too late, but I think they are nice. So he's in CISA, and it's called Notes on Bethe Ansatz. You have to go to his webpage and look for lecture notes. I mean, it's not immediate. But again, I don't think that he gives less details than what I gave you yesterday, but okay. So if we apply this procedure for this matrix, we shall end up with Bethe equations, which look very similar to the ones we had before. But of course, we'll have this exponential mu creeping somewhere. It will appear in the equations. So I'll rewrite the equations. But if you allow me, I will make a small change of notation because I don't want to carry on this P and Q everywhere. There's an overall time scale. Okay? So if I divide time by a factor P, I can always take the forward jump as 1 and the backward jump as Q over P. Okay, it's trivial. And now I'll make a major pedagogical mistake, but it's nice to have that. I will call Q over P, which is the asymmetry factor, as X. So it's not the position of a particle. Okay, it's not x1, xn. Sorry for that, but the position of the particle will disappear because we only use them to derive the Bethe equations, which I'm not going to do again. And now we don't have any x. So x now denotes the asymmetry parameter and not a coordinate. And the Bethe equations for I equal 1 to L are given by zi to the power L is equal to the product of minus 1 to the power n minus 1 j equal from 1 to n. So again, you'll see the similar form, but of course, some mu's will enter the game. Zi, zj minus, so now, yeah, p is 1 and q is x. zi plus exponential mu divided by the same thing almost, zi zj minus 1 plus x zj plus exponential mu. Okay, here they are. And as I told to some of you in many, many papers, people just start with these equations. There have been a huge effort, even by some extremely sophisticated people, even by somebody who's called Lagrange, who's one of the very, very, very great mathematicians alive. Maybe you heard about this Lagrange program, to have tried to analyze these equations, because these equations, if you just put the denominator here, they are algebraic equations. So for mathematicians, they fall into the realm of algebraic geometry, and counting the number of solutions, the position of solutions, whether they are real, complex, and so on, is a formidably difficult problem. Of course, we are not going to do it. I'm totally unable to do that. I just want to compute the largest eigenvalue. But anyway, any eigenvalue will be given by this formula, exponential mu sum over 1 over zi's plus exponential minus mu times x now sum over zi's, sum over I, minus n, p plus q becomes 1 plus x. And we want to find the maximal one. We're interested in the maxima. These are all the eigenvalues. So the program a priori, suppose you have a supercomputer, you put these equations, you find all solutions, z1, zn, you plug them here, and then you extract the biggest eigenvalue. This is totally impossible to do, of course. I mean, but if for systems up to size, as I told you, 50 or 100, Mathematica can solve these equations. But even then, I mean, plugging back and so on, sorting the maximal eigenvalue is not trivial. Okay, these are highly coupled equations. So it's highly coupled unless x equal to 0. Because if x is equal to 0, the same thing happens as I told you the other day, this Cassini ovals and so on. If x equal to 0, the quadratic term will disappear. You can bring the zi to the power, this thing to the power n here. So it will become a polynomial in zi. And then the right-hand side, which doesn't contain that anymore, will be the product of all exponential mu minus zij's, which is independent from I. So you can play the same game with Cassini ovals. Yeah. So, yeah. So you have an equation here for z1, z2, zn. Here? Here? Yeah. So I write an equation for z1. I write an equation for z2. I write an equation for zn. I have n equations. Oh, sorry. Yeah. Sorry. Yeah. And here also. Okay. So unless x equal to 0, this doesn't decouple. And even for x equal to 0, it's a difficult task to solve these equations. So I'm going to tell you about another way of calculating that. Just to tell you the story, x equal to 0 was solved 10, 15 years ago by Derrida Leibowitz. It's a PRL. It's a very nice paper, but which uses quite a lot of complex analysis, contour integrals, very tricky, very astute, as many of the papers of these people are, but not elementary. And x equal to 0 is a Tarzan case, but somehow what would have been interesting in this problem is to compute for all x, and especially x going to one limit. Because x going to one limit is the limit of the symmetric problem. The symmetric problem is equilibrium, and the continuous limit is obtained only when you make x going to 1 plus epsilon, epsilon being of the size of 1 over L. So the good continuous limit is really in the vicinity of x equal to 1, just like as in the case of a random walker. You have to bias the hops of the jumping rates of the random walker as 1 plus epsilon and 1 minus epsilon, where epsilon scales as the size of the lattice to have a right continuous limit, a good continuous limit. And here x going to 1 is a formidably complicated set of equations. So what I'm going to do in the coming 10 minutes, and this is going to be maybe not the last technical part, but yeah, I mean, it's not going to be as technical for the rest of the lecture. What I want to do is to show you how to get from these equations to a single functional equation. So this is called, oh sorry, I didn't give you the name. This procedure that I told you about is called coordinate Bethe Ansatz, because we used coordinates, x1, x2, xn. So coordinate Bethe Ansatz. I'm going to derive from the coordinate Bethe Ansatz a much more elegant and compact equation, a unique, a single equation, which is called a functional Bethe Ansatz equation. Okay? So this will provide you an example of a functional Bethe Ansatz equation, and I will start for the coordinate and get the function. Usually it's not done like that. You can get the functional Bethe Ansatz immediately, but using much more abstract tools. So, but then you have to teach these tools, and it will take 2 hours to teach these tools. So what I will do is not standard, but at least the equation I will obtain will be a typical functional Bethe Ansatz equation. So the idea is, remember, you don't have to do the coordinate thing to get the functional equation, but if you want to get the functional equation directly, you have to use much more elaborate technology. This I will not do. So I will do this kind of pedestrian path, but at least you will see what it looks like. And the nice thing is that once we have this this functional Bethe Ansatz, first of all, it looks much nicer, and then it becomes solvable. So yes, as I told you, this was done in 97, 98, but the general x case, so even not only x going to 1, the general x case was just blocked for many years, and it was done only, I don't remember, 5-6 years ago by Sylvain Prolac, who was at that time, who's now faculty in Toulouse. At that time it was his Ph.D. thesis, an extremely bright Ph.D. student who was doing his Ph.D. with me. And a part of his Ph.D. was understanding how to solve the general x equations here. And it was really a highly non-trivial problem. Very bright people, including these ones, were trying to solve it, and it was blocked. Okay, so let's see how it works for general x. Yeah, let's do the procedure. What else do I want to say about this? Yeah, you can find the references easily. Okay, so again, going to the functional Bethe Ansatz, we look here a bit, I mean, why are you doing that, and so on. And it doesn't look like a method, but more a kind of specific trick which is restricted to this model. It is not the case, but it's the easiest way to tell you how to do it. So first of all, there is a change of variable to do here, because we don't like these quadratic things. Okay? Change of variable is in fact quite classical in this game, and so I'm not going to give you all details, but believe me, this is again 1 and not lambda. If I write these variables, which appear in many papers, or playing around with these things, you will finally guess them by yourself. These equations start looking much simpler. So these equations, which were quite horrible, become less horrible. And they look like that. Yeah, they become somehow much more harmonious. They become like that in the y variables. What we have gained is that second order terms have been totally eliminated. And always I1 to n. Okay, so what can you say by looking at these equations or at the original Bethe equations? What do you observe? There is one observation which is trivial but extremely important, and it's always the case almost. The equations are very symmetric in Zi, Zj. They are very, very symmetric. I mean, all the Zijs play the same role. For all yi's, I have similar equations. It's very, very harmonious. Unfortunately, it's again highly coupled. Okay? So here comes a nice trick, and this is the kind of trick when you find it once in your life, you never forget the day you've thought about it. I just wish that it will happen to all of you at least once in your life. So you stare at these equations, you don't know how to solve them. Okay? And then you say, okay, it's so harmonious that I will change the name of the things. And you replace your yi here. Let's call it t. Okay? So my Bethe equations are just this equation for t, but by putting t equal to y1, y2, yn. Not a big deal. It's just to save some place. Okay? But now if you look at this equation and you change the denominators, you just rewrite it as a single variable equation in t, but as a polynomial equation. This you can do. I mean, this is, all this is a kind of 8th class algebra. So you can always write this equation as exponential L mu 1 minus t to the power L times the product. I will put it in red, you will see why later. Product of xt minus yj. So of course these are still here. J equal to 1 to n. Okay? Plus 1 minus xt to the power L, product of 1 equal to 1 to n, t minus xj, xyj equal to 0. You agree that this is exactly the same equation as here, if I didn't make any mistake in copying. Did I make a mistake in? Oh yeah, it's a product. Here? No, it's a definition, it's a polynomial. It's a name. Sorry, I can call it A of t, but why would you like this to be a product? It's, you want another name for it? Or is P okay? It's a polynomial. It's a polynomial of degree, and the Bethe equations are just that this polynomial is equal to 0. You agree with that? Yes? I mean, I'm doing nothing. Just these equations are these ones. But now we know that y1, y2, yn are roots of the polynomial. y1, this is the Bethe equations, are roots of pt. of this polynomial P of t. Okay? What does it mean? It means that the polynomial Q of t, which is defined by the product 1 to n t minus y I, has to divide P of t. Again, suppose that the roots are different and so on, generically. You follow? Yes? If I know the roots of a polynomial, I know that this product of these simple terms has to divide the polynomial. Yeah? This is elementary. By the way, this is nothing but the generating function of the symmetric polynomials in Y. Okay. But look at that. Q appears here. This is Q of xt. Okay? And Q appears here. This is Q of t over x times x to the power n. You can just check it. So Q of t divides this very simple polynomial times qxt, this very simple plus this very simple polynomial q times xn qt over x. So this tells you that there is a ratio. In other words, there exists another polynomial r of t. There exists a polynomial. You can compute the degree easily. R of t such that, so again I wish I could use the upper part of the such that qt rt is equal to exponential L mu 1 minus t to the power L qxt plus the rest. I probably forgot, no, I didn't forget anything. Q of You agree with that? Yes? Well, this is the functional Bethe Ansatz equation. This is a functional equation for two polynomials. The beta roots have completely disappeared. It's much more elegant than writing what I have written all before. This is the functional Bethe Ansatz. So it did appear before, of course, in other contexts, 6 vertex models, Baxter. In fact, it is called Baxter's Q equation in other communities, because it's really him who found it. It's called Baxter's Q equation. And it's perfectly equivalent to the Bethe Ansatz equation. Because, for example, if you substitute yi, any yi, which is a root of q of t, so the left-hand side will be equal to 0. Put yi here. This will give you exactly, using this definition, the Bethe equations that I wrote before. So this is perfectly equivalent. But what have we gained here? First of all, it's an equation for only one unknown. It's a function, but it's a polynomial of q of t. We don't have to calculate any root. Calculating roots is very complicated. The only thing we need to calculate is to compute two polynomials. So for example, for a system of small size, you just write these polynomials and you know the degree. You even know that the dominant degree is 1, t to the power n plus. So just write unknown coefficients for q and t, q and r. So qt is tn plus an minus 1 tn minus 1 plus an minus 2 tn minus 2 plus a1t plus a0. R of t is t to some power, okay, plus b n minus, it's not n, b t k minus 1 and so on. So you have, in fact, equations for the coefficients of these polynomials, and the equations are at most quadratic. One coefficient here, one coefficient here, linear, linear. It's infinitely more simple. Just and this you can solve for systems of size hundreds without having to extract any root. The thing is that the roots of the Bethe equations are extremely complex objects. They live in the complex plane, they are complicated, but these polynomials, which contain only symmetric functions of the root, they are very simple. The coefficients are simple. Okay, and this is a trick which allows you, in fact, to solve all the cases. Not only x equal to 0, but even x arbitrary. So, okay, I intended to enter into the details, maybe I will not. I will just give you one illustration of the technique, but again I insist, here I got this equation in a kind of very indirect way, so you may think that it's only for exclusion process, you have to do all this horrible procedure to get it. It's not true. For integrable models, you can get this kind of equations, but using a more powerful technology, which is called the algebraic Bethe Ansatz technology, which I didn't teach you. But if one day some of you need to get there, you'll have to spend 1 or 2 weeks learning about algebraic Bethe Ansatz, or you'll call me again, I'll teach you the algebraic Bethe Ansatz. I'm joking. You'll call some people who are more knowledgeable in algebraic Bethe Ansatz. They will teach you, and you'll learn how to get this equation directly. Okay? I didn't know about that. So we did it this way, by finding this nice trick, but it's not necessary. But okay, I mean, it works at least. And I think for pedagogical reasons, it's very nice, because you see things in a kind of elementary way. Anyway, so how do we use these equations? How do we case x equal to 0? Okay. So here again, we don't need to do that. We could use Cassini ovals and all the things, complex analysis. But you'll see here that it becomes very nice. So if x equal to 0, this becomes this functional Bethe Ansatz equation becomes the following. And you will see, Abhishek, how things can be eliminated. Okay, I will tell you what B is. Well, B is just exponential L mu Q of 0 minus 1 to the power n minus 1. This guy is here because of some sign reasons later. You need to put it. Plus, so here you have to be a bit careful, but it's very simple. This is a polynomial of degree n. There is an xn here. So only the highest degree will survive. And Q is a product of t minus yj's. So it starts with t to the power n. So the only thing which remains here is 1. It's t to the power n. The limit is not singular. It's a simple limit. Okay? So here's the functional Bethe Ansatz equation in the case of Tarzan. Yes? And, okay, I didn't tell you, but you can, I mean, then you have some massaging to do. But we want the eigenvalue E of mu. I gave you an expression for the eigenvalues, sum over zi's, sum over 1 over zi's. You have to rewrite it in terms of y's. And then we have to reinterpret it in terms of these polynomials. The beautiful thing is that everything that we wrote in terms of the root of the Bethe equations, because everything we wrote was totally symmetric, can be written in a very simple way in terms of these polynomials. So in fact, you will find that E of mu, in this case, is nothing but Q prime of 1 over Q of 1 minus n. There is nothing mysterious here. I mean, Q prime of 1 over Q of 1 is something like 1 minus x yi, or 1, something like that. And this is just the expression. You start with your expression for E. You substitute y's in terms of z's. You get a symmetric rational function, which is very simple. And you can just identify. Now, using this equation for t equal to 1, you see that something special happens. You can, in fact, compute R of 1 in terms of Q of 1. Again, this is this is 8th degree level of mathematics. There is really nothing here. This could be a very nice exam for matriculation or playing with polynomials, and so this is completely elementary. So we need to compute that. And the other thing we know, which is maybe slightly tricky, but because I didn't tell you about it, if you look at the Bethe equations, you remember we had z1 to the power L equals something, z2 to the power L equal to something else. There's one very important property of these Bethe equations is z1 zn to the power L is equal to 1. Well, this is a trivial property. This is a property that we would call periodicity in a naive way. It means that if I translate all the position of the particles by L, I should get the same thing. But this is not the elaborate periodicity that we talked about yesterday. But of course this is true. This just tells you that the system is periodic. Okay? Another way of saying it is that we have this. But this tells you nothing, if you think about it, that the translation operator commutes with the Markov evolution of the exclusion process. This is just, you see, if we write again exponential a chi1 and so on, this is just the fact that plane waves, yeah? X equal to 1 is a symmetric case. Complicated, but it will remain symmetric in the y variables. Remember that in the change of variable between z's and y's, I had some exponential mu coming. Okay, so it will give me a condition which is symmetric in the y's equal to some exponential mu. Anything which is symmetric in the y's, I can write it in terms of this polynomial q or r. So believe me, it gives you a condition, and because you have products, you can take logs, and logs are obtained by taking q primes over q. This is nothing but the logarithmic derivative. Anyway, I don't do it, but this is totally elementary. You get another equation which is mu equal to 1 over n, or 1 over n or 1 over L. 1 over n, where n is the number of particles, log of r of 1. So the idea is, if you solve the functional Bethe Ansatz equation, and if you know the values of q and r, or even only of r, by plugging it here, you get the energy, and here you get mu as a function of r of 1. So you get a way of determining the unknown constant that somehow was the one which was lacking before when Abhishek asked his question, that r is not fully determined. In fact, it is fully determined up to a constant, and this fixes the constant. R of 1 is n exponential n mu 1. Okay, I'm not going to do this into the details, but the beautiful thing is that all this machinery being written, there's nothing left to do. It's almost trivial now. It's almost automatic. There's almost nothing left to do to solve this equation. Remember that q of 0 is nothing but the product of all the minus yi's, I equals 1 to n. And there's another thing, again, there's no subtlety, but at each point you have to be a bit careful. What happens is that when mu is very small, because we want a mu expansion of these things. When mu is 0, you're back to your Markov matrix. Okay? You want to calculate the ground state of your Markov matrix. But this you already know. It's uniform. All the probabilities are the same. Okay? Then this knowledge you have to use. In fact, when mu is equal to 0, or when mu goes to 0, all the Bethe roots goes to 1. By the change of variable, all the y's goes to 0. Because in the change of variables, there was 1 minus zi, and so on. So Q of 0 goes to 0 when mu goes to 0, and B goes to 0 also. The only thing I want to say is that B is small in this game. Mu small, B small. This you have to realize at a certain state. B small. Okay? Mu is given, you're right. Mu is a fugacity, so mu is a conjugate variable to the current. So if you want to compute the probability of having a given current, even if it's atypical, this fixes the fugacity mu, and it's R of 1 which is given. So now let's finish that. You will see there's nothing much to do, so effort has been saved by all this procedure. I just divide by t to the power n, and I get this. R of t. By the way, Q is of degree n, and R is of degree L minus n, as you can see from the equation. Okay, to get this. This is a constant. You follow me? Divided by t to the power n. Okay? So this is a polynomial of degree n divided by t to the power n. So this is a polynomial in 1 over t. Okay? Yes? So in this equation, yes, but not in the Tarzan case. Okay, so I'm doing the Tarzan case, which is simpler, but you're right. Here we'll have to be a bit careful, but it will work a bit the same. I want to do this case completely just to show how it works. Then I will give the results for the general case, which is more complicated technically, but in fact it amounts to very much the same. So here R is of degree L minus n, and this is a polynomial of degree n, which starts at Tn, plus Tn minus 1, Tn minus 2. So this is a polynomial in 1 over t, 1 over t squared, 1 over Tn. I just divide a polynomial of degree n by Tn. So, okay? And this is a real polynomial. This is a polynomial in 1t, t squared, tl minus 1, l minus n. Okay? So what I'm going to do is just to take the log of this equation. So I just take the log. So it's the sum of the logs. And it's a log here. Okay? This is, well, this is not so complicated. This is just a polynomial of degree L divided by a polynomial of degree n. It contains terms which have both positive and negative degrees in t. Okay? 1 over Tn, but because L is bigger than n, so when I go to higher degrees, I can compensate for the denominator. But b is small, so I can expand this in terms of b. If I'm not I just copy it because I don't remember by heart the series for the log, what I do, but if I just write the log series, it's something like that. One minus b to the power k, 1 minus t. Here I use the fact that b is small. Otherwise, I wouldn't have bothered telling you that. Okay? Sum over k from 1 to infinity. I just expand this log. So now can you tell me what is R of t and what is Q of t? It's done. We know what they are. Can anybody tell me? And this contains only negative powers of t. So this contains positive powers of t, and this only powers of 1 over t when expanded. So it's even we know it's 1 plus something over t because q starts at t to the power n plus something at t squared. So the idea is simply that now I can again expand this. This is just the binomial theorem. And all positive orders correspond to r of t, or log of r of t, and all negative orders correspond to this. So I just split this series into positive and negative powers, and I know what is q of t over t and what is r of t. Okay? The beautiful thing is I didn't tell you, I don't even need to know r and q, because here it's log, and here's the derivative of the log. So if I know what is log q and log r, I'm happy. So again, the key point is that by separating positive and negative powers in this series, I can just identify. Okay? So here it is a power series with positive and negative powers. So I will have some k positive powers, tk, and k negative powers. Okay, you have to be careful with the zero powers, they don't occur, and so on. You have to check these things. Okay, let's say k positive t minus k, and I just identify, and I get them. This you can do. And in the end, I substitute that. So now doing that just takes a few lines. I'm not going to do it, but it's really, you know, it starts here, and it ends here. It's just, you just expand this by binomial theorem and count when you just write this as sum of KL Q TQ minus 1 to the power Q, and when Q is bigger than Kn, it's a positive power. When it's less, it's a negative power. When you just identify. So in the end, and now we shall end with something, we can start talking about physics, and I can try to connect this to what Satya told us this morning. But in the end, we finish up with a series for E of mu and a series of for mu itself in terms of this parameter B. Okay? So we end up with very nice looking series, which are in fact quite simple. So again, this series was first derived by Lebowitz and Derrida, but using a different, very different technique, which could not be generalized to arbitrary x, which was only valid for x equal to 0. That's why also in this technique, the x equal to 0 case is much simpler, but it can be generalized, the same kind of procedure, and has been generalized fully by Sylvain Prolac. But you end up with this series. And as you see, this is extremely explicit. I mean, there is no unknown factors or things like that. And E is given by minus sum k equal 1 to infinity kl minus 2 kn minus 1 bk over k. So you'll tell me that you're not happy because you want the function E of mu and you don't want something in terms of an unknown parameter. You want E of mu. So for example here it starts like mu is 1 minus L, so for k equal to 1 Lk B plus so and so. Just putting the first term and so. So what you have to do, which cannot be done explicitly in general, is to invert this theory, compute B as a function of mu, and put it back here. Yes? But we don't need to do that. For example, as I told you, if I make a Taylor expansion of E of mu, so E1 mu is E2 mu square over 2, E3 mu cube over factorial 3, and so on. Do you remember what is the meaning of E1, E2, E3? They are the cumulants of the current. E1 is the average of the total current, E2 is the variance, E3 is the third cumulant. And in fact, you just need to do this order by order. If I do the substitution for getting higher orders, so this is just simple, it's linear, I keep the first order, I get E1. If I keep only the first two orders in each equation, I get easily E2, and so on and so on. So it's an iterative procedure. If I want to calculate the kth cumulant, I just need to keep the key first orders in both equations. So this gives you, of course, the average value of the current. E1 is the average value of yt. Well, there's a factor t, you remember? Because it was exponential t e of mu in the long time limit. And this is just given by n L minus n over L minus 1, which in the large L limit, keeping the density fixed, is given by L rho 1 minus rho. This is trivial. You don't need to do all that to get this. First of all, this you can just say that this is the current through one bound, rho 1 minus rho. Side occupied, side empty. This is the mean field current, and I multiply by the number of bonds. Even this is very simple to obtain by just counting. The second, which is the variance, which is E2, is much less simple to obtain by elementary means. In fact, it was obtained before by a complicated calculation using the matrix Ansatz. It's a complicated calculation. And the third one was out of reach, whereas here it's very simple. I just write the formula not for you to learn it by heart, but just to tell you that it's totally explicit. The nice thing is that if you go to large size systems, you can get the scaling out by Stirling, and it gives you something like that. Okay, and so on and so on. And you can find the scaling of the kth cumulant. So the kth cumulant will scale like the cumulant like L to the power 3 over 2 k minus 1 for k bigger than 1, strictly bigger than 1. But this is not the end of the story. In fact, it becomes much nicer after. We are interested in the large n limit, okay, and large L limit. So all these binomials, these are binomials, you can simplify them by Stirling. And if you simplify them by Stirling, you get very, very, very simple functions that in fact you have already encountered during your studies. If you simplify these two series, you get series which look like that. You will have to change the value of the parameter, but this is not important because the parameter b is only dummy. But you'll get series which, so maybe I should write them in another way, or maybe not. What is the nicest way to write them? Okay, you get series which look like that. You'll have to change the definition of mu and so on, but the series for mu will become like something. Just use Stirling. And you have to change the definition to incorporate some constants. I just want to give you the structure. And the series for E will become this one. And that's why speaking English for people who are educated in France is a nightmare, because not 90%, 50% of the words are just the same, but just pronounced completely in a different way. So somehow you have to use your usual language, but by twisting the pronunciation. So this is, I don't know what, G of J or J of G, okay, something like that. And this is obtained by making a Legendre transform of E of mu. I'm not telling you but you know the formulas for Legendre transform, or at least it should ring a bell. These are the formulas for Legendre transform. So remember, I know E of mu from this analysis, so that's how we'll get G of J. And by using the scaling and the Stirling and so on, you find that G of J is given by something like that. So this formula is maybe worth examining, and we'll make some pictures. This is a typical value, and just it's a definition. You can always scale things. Rho is finite. Rho is the density. So it takes this form. And now we have to, so this comes from the mathematical analysis of, and we are looking at large deviations. So this is a large deviation function of order 1. So let's plot what's going on. Let's plot this function. So now the analogy with what Satya told us should become slowly and slowly more clear. It will become even more clear this afternoon, because I will show you how you get an integral for these quantities, which is very, very similar to the Wigner-Dyson integral that for the eigenvalues that Satya told us about. So now let's plot this function h of x, and you will find some resembling features. So here, because I've put this, just translated, the typical value now means is 0, this equal to this. So it's centered at 0. Okay. So I should draw it careful way. So here it's, okay, it should be 0 here, sorry. So it's quadratic here. It grows like x to the power 3 over 2 here, and x to the power 5 over 2 here. So it's non-symmetric. It should start ringing a bell here. So it's Q. And as we saw this morning, if we do expansion near the quadratic place, we should find the variance. So you see there's a 1 over L, 3 over 2, but in fact H also contains an L. So here the variance, I mean, no, it doesn't. This 1 over 3 over 2 will give us the variance. So the variance, it will give a Gaussian behavior. It's a Gaussian region with variance L, 3 over 2. So this is the Gaussian region. So here it looks much smoother than what Satya told us this morning. A priori, there is no singularity here, but we'll make one appear soon. Okay. So this is the behavior of, and this is for values of j's of this thing which are finite. So I take this, of course, when I compute a function, I compute it for arguments which are finite. So it means that j is equal to L rho 1 minus rho plus some finite number. So I'm looking at finite large deviations from this large average value, typical value. Okay? Not yet. It will come. Yeah, because it's not exactly the same. And in fact, I won't be able to push it to the end, but you will see it coming if I can take 10 minutes. You should see it coming. Okay, the problem with that, you see there is a huge current here, which is proportional to the size. All this is because we counted the total current through all the bounds. This is not the right variable. This is not the right variable. We should count, in fact, a local current. So let's work with the local current. So we should work with the local current through one bound, which I will call Qt. Okay, this is a local current. And what is Qt? It's just Yt over L. Okay, so here things will become a bit more complicated. I'm interested in large deviations of this local current. Yes? So I want to ask the same question, but now with Qt. what is the probability that Qt over T has some value, I should call it more now small j. So the average value of the local current, we know it's rho 1 minus rho. This is just the AZEP current. Okay? So what is the probability that it takes its average value plus some small j? So again, it's some function h. No, what did I call it? Minus t. And I should find another. Well, let's call it h of small j. But now one has to be careful, because if I look at finite large deviation for small qt, they mean large deviations of order L for yt, just because yt is L times qt. So this just means that yt over t is L rho 1 minus rho plus L small j. Okay? So finite deviations of the local current mean extensive deviations of the global current. So I have to be very careful, because here somehow I will have to take capital J of the order L small j. So I will have to evaluate this function for very, very, very large values of the argument. So here one has to be very careful with the asymptotics. What will happen is that the infinity things will get shrunk to 0. Do you get this point? This is important. Do you get it or not? No. Did you get this thing? These are the large deviations of the total current. Okay? So this is, maybe I should put what I'm writing here. This is the variable which I call psi, although it's a very bad name because psi will come back, and this is h of psi. I just plot this function. This function is obtained by a magic procedure using Bethe Ansatz function, Bethe Ansatz, whatever you like. The function exists. It can be put in a computer. You plot it. You can get its asymptotic behavior. It's like that. Okay? But what does it represent? It represents large deviations of my quantity yt over t. What is yt? Yt is the total number of jumps, positive jumps minus negative jumps, in my exclusion process during time t, between 0 and t, for all the particles in all the system. Whenever a jump occurs somewhere, I add +1 to yt if the jump is in the positive direction. I subtract 1 from yt if the jump is in the negative direction. I do the large deviation, I get this. Okay? But of course, this tells me that psi has to be finite. In this picture, psi is finite. It goes from 0 to I don't know what, finite. When you calculate a function, you always calculate it for finite values. So this tells you what is the probability that yt over t, if I now spell out what this means, is equal to L rho, this is j. So it's L rho 1 minus rho plus rho 1 minus rho psi is this function exponential minus t g of psi. Okay? Because in fact g of j is a function of psi. You get it? And if psi is very big and positive, well, this thing will behave like psi to the power 5 over 2. If psi is very big and negative, it will behave like 3 over 2. Okay? Now I want from this information to get another information, which is more physical and which is closely related. So we should not, I mean, we're not crazy. We're not going to calculation again, Bethe Ansatz only for one bound. So now I'm interested. I have my exclusion process. It's a very, very big ring, extremely big in the large size system limit. I sit here between sites 1 and 2. I look here only, locally, and I have a local observable which I call small qt. And this small qt counts how many particles have gone through this bound between time 0 and t. again positive minus negative. So it's the total current, total integrated current through this board. Total charge that have gone from left to right, but of course there is a sign. Okay, from 1 to 2 with a sign. Well, Qt and Yt, they can be connected by this relation. Because we are in the long time limit, here there is a small caveat, one has to be careful, but again we consider a system which is of size L in the limit t large, and for the aficionados, I take the limit large t before taking the limit of large L. So I first consider, you see here we have solved the problem for any given value of L in the large t limit, and then taken the limit of large systems. This is very important, in fact, the order of technical limits. So I want to, from this knowledge, I want to deduce a knowledge for my physical variable. I want to deduce a large deviation function for Qt. So I want to ask what is the probability that Qt over t take its average value plus some deviation. This is the large deviation thing. I can always add a constant in the large deviation definition. It's not important. Usually you would call it something, small q. It's not important. I can add a number to it. I can just shift it. Well, because of this relation, I can translate this as the probability for Yt over t equal to L rho 1 minus rho plus L small j. Yes? And what I know is this probability by this function. Yes? In fact, more precisely, I know, if I just use this relation, I know this. Yeah? So how do you compare this with this? Well, okay, j, I can always define it as rho 1 minus rho times j tilde. This is not important. The only problem here is that psi takes only finite values from minus infinity to plus infinity. Okay? Whereas here, I have a factor L, which is very large. So somehow, I have to evaluate this function for very, very large values of the argument. Yes? When I evaluate these functions for very, very large values of the argument, it's just as if I had a function of psi. Now I have to calculate the function of L psi with L very big. So it means that it will just shrink the picture by 1 over L. All this picture will get shrunk. Shrunk, shrunk, shrunk. Okay? Tell me if I make a mistake. I mean, it's not natural to me. Okay, so I shrink it, and what do I get? And here the Satya singularity appears almost the same as before, in fact even more than what we think. In fact, if I do this, I will have to be careful whether this argument is positive or negative, because I don't have the same behavior to the right and to the left. Okay? So if I do this slightly more carefully, what you will see is that this thing, so I forget about all this rescaling thing and so on, I will have two behaviors, one on the left and one on the right. So let's write it again, which in fact come from the general behavior that we got. But one has to be more careful with the asymptotic analysis. So I will have two behaviors, h plus or minus, right or left, with h plus of j is in fact, and one has to be careful in the large asymptotics, L j phi over 2. There is a factor L which will appear, and h minus of j is of order g j 3 over 2. So this is for g j negative and j positive. It comes from a finer analysis of the function capital H that was written here. Okay? And now if we make a picture, by shrinking that picture by almost an infinite factor, because L is extremely big, and we put H here, so we will have H plus in the positive branch, and it will be here of the order of L 5/2, and here it will be less j 3/2. And you can talk about the asymptotic behavior here and here, and of course it will be, you see, the infinity of this function has been brought back in the finite region. So to get the asymptotic of that function, somehow you have to do the super asymptotic of this function. I'm not going to do it. It's doable. Okay? So here you have a non-analytic behavior. Which is similar to the one that Satya told us about. And in fact, it is more than similar. It is in fact very closely related. If I can take 5 minutes more, I will try to patch it with what Satya told us. I will try because I was not able to do it completely. First of all, can you tell me, could you give me some kind of rationale? It's not easy. It's easy when you know the answer. Why there is such a big difference? For example, why is it more difficult to get positive currents than negative currents in this exclusion, in this totally asymmetric exclusion process? This really tells you that that's the case. First of all, the power is bigger, and there is a huge factor L here. L is very, very big. So why is it more difficult to get large deviations on the positive side rather than on the negative side? It's a very simple reason, which has nothing to do with Bethe Ansatz. It's common sense reason. Yes, yes. So how do you reduce the current in the totally asymmetric exclusion process? How do you manage to reduce the current through a bond? Yes. In fact, a very simple way to reduce the current in this bond is just to say there is a particle here which is lazy and which remains. It's a single particle effect, just like what we had in this droplet thing. Okay, I'm pushing maybe too far, although it's not completely the case, because there is a kind of thing like that with the beta roots. There is one beta root which goes from the droplet, but it's a single particle effect. One particle is lazy, the other ones are living their life, but this one is enough to block this poor bond, because the one here has to wait that this one goes away to be able to jump. Okay? Whereas to increase the current through this bond 1, 2, I have to accelerate all the particles. So decrease the current is a single particle effect. So to decrease the current, one particle is enough, one blocking particle is enough. Whereas to increase the current, that's the factor L, it is a collective effect. So this gives you a rationale a bit why it should be skew and so on and so on. Okay? Now let's patch this with Tracy-Widom, because it has a relation with Tracy-Widom. There's something else we want to say. I mean, we are talking about large size systems, L going to infinity. Why shouldn't we start from the very beginning from an infinite system? Why do we? So as I told you, one has to be very careful, because we took the time going to infinity limit first, and then the large size system later. But it's also natural, and there has been a huge amount of work. What should I remove? Remove this one. 9, Z, and I have a lattice. So many different things happen, but it should be related in some way. So I have an infinite system from the very beginning. I have side 0 is the totally asymmetric exclusion process. And at time t equal to 0, all the particles are lying on the negative numbers. It's full with particles there. And I start my system. So this one will jump and so on. And it will start spreading. There will be a front spreading. The shape of the front is well known. And I call, this is site 1, I call Qt it's a Tarzan, okay, for the moment being. So Qt is just the number of particles that have jumped through bond 0, 1 between time 0 and t. So it's the total integrated current between time 0 and t. Qt is the total current through 0, 1 between 0 integrated current, total charge that has passed through this bond from left to right. It's a Tarzan. And the initial condition is very important in this game because it's an infinite system. So in fact, it takes an infinite amount of time to relax. It never relaxes. The system keeps a memory of its initial condition. So I just specify that I put everybody to the left. Okay? Then it's possible to show that Qt, and I will use exactly the same notation almost as Satya did this morning. Well, it's still the morning. No, it's not the morning anymore. Qt, you can show that on average it grows like t over 4. This is mindful of the maximal current phase of the exclusion process. There's a very simple way to get this t over 4. In fact, if you wait long enough, your front here, so here you start with a step, 1 density is 0, and if you wait long enough, it will smoothen, so it will become a fan thing. I don't know the name exactly. And the average density in this region will be 1/2. This you can buy. The average density here will be 1/2 near the 0, 1 bond. And what is the current? It is rho 1 minus rho. 1/2 times 1 minus 1/2 is 1/4. So this is the average current. 1/4 and the integrated current t over 4. You don't need Bethe Ansatz to get there. But what you will have is that this is of course a random variable. I extract the leading term. There is a subdominant term of order t 1/3. We can call this KPZ scaling. It is related to the 3 over 2 the dynamical exponent that Deepak Dhar computed, but multiplied by a random variable here. Not the same one, sorry, but I keep this. How did you call it this morning, this random? Huh? Chi. Okay, so I call it chi to be really consistent. So it's a random variable. Which has a law. It's a random variable. It's not a Gaussian. Guess what it is? Well, you know now. It's a Tracy-Widom law. It's a Tracy-Widom variable. Okay? So this chi, as Satya told us, there are 3 or even more types of Tracy-Widom, beta 1, 2, 3, 1, 2, 4. So this is a beta equal to 2 Tracy-Widom. So there is a deep relation with random matrices here. So it's a beta equal to 2 Tracy-Widom law, which is related to RRI. So I think it's also called an RRI variable. And the probability that chi is less or equal than a value s is given by the same function f2. So there is a mismatch maybe in the notation, but it's not really important. f2 of minus s, but it's the same f2. Maybe there is a sign from left to right, the same f2 that Satya wrote. So what is this f2? If I plot the distribution, so this is the integrated distribution, I need to plot minus f2 prime of minus s. This is a distribution of chi, probability that chi is equal to s. And now you get your tails and so on. So it's on the positive side, that's why there is a minus sign and so on. This is just small things. And you get your, so I'm taking the values for beta equal to 2, s cube here, and the other tail. So probably my picture is completely wrong, but 3 over 2. Because this is exactly what we learned this morning. Okay? So now the question is, I have this picture on the infinite system, Tracy-Widom, we know the asymptotics. I have told you many things about this H plus, H minus, Bethe Ansatz. How do all these things paste together? Because more or less, okay, maybe they don't paste perfectly, But as we saw this morning, there was this tracy rhythm region, there was the large deviations, and Satya was able to match them. So there should be some matching thing here also. There should be some way of going from this picture, which uses results from random matrix theory. Maybe if we have time this afternoon, I will tell you more precisely where it comes from. And the picture that we got before on the finite size system, and so on and so on. So I'm getting longer and longer, but I have half a page to tell, and then we'll go for lunch. Let's analyze what he says. So this says really that the probability that the number of particles having crossed the first bond during time t in the infinite system will behave is the same thing as the probability of psi being equal to j 3/2 just by translating what's going here. Okay? And if I use now not psi chi, sorry. Okay? And if I use the results there, I will get that for j negative, I got exponential -4 just by substituting the value of j into the tracy rhythm asymptotics, 3/2. And for j positive, exponential minus t square over 12 j cubed. So again, t is the n of this morning somehow, and this is the n square. So this is really the same thing as, g plus or phi plus, you call it, phi plus and phi minus, or maybe no, this is phi minus of this morning in Satya's notations. So again, we have two behaviors on the left and on the right, and two different scalings also. So you see, this is a kind of normal large deviation behavior with t, but here it's t square, just like n and n square. So it's not always t. It can be square root of t, t square, and so on and so on. And now what we want to do is to patch this to what we saw this morning. And what we saw this morning, so there's something else I wanted to say, but maybe it's not, okay. This afternoon, maybe if we can not erase the blackboard, this afternoon I will start by saying something which is more elementary. I will give you an argument which must be known in the community, but I learned it from Paul Krapivsky, and I find it very beautiful. For these exponents, y minus s cube here, and y minus s3/2 here, without having to do any pain levé or in knowing about tracy rhythm, by just like this Lifshitz argument that Satya developed this morning, there's a simple physical reasoning on the TZAP picture, which gives you not at all the numbers, but at least the power laws. But this has nothing to do with the matching I want to do, but I want to keep this picture so that I don't have to draw it again. So the question is, how does this match with the finite size? So how does all this match? People will be able to help me to do the matching fully. And here the grown-up are allowed to play, because it's probably... Sorry? Yeah, I don't think so. I don't think so. The super large deviations, I don't think they are known. I'm not sure. But as far as I know, these are the standard results for the ASAP. Yeah. So matching with the finite system. So remember what I erased. When small j was negative, I had the same behavior. If you look at what I wrote 5 minutes, 10 minutes ago, the behavior was the same. So this, there is no problem. It matches perfectly. I don't know about the constants, but it matches perfectly. The problem is for positive j. You remember we had a factor L. We had something like that, exponential minus t L g j 5 over 2. And here we have something which looks like t square j cube. So it's not exactly the same. But somehow you see there is a factor L here, which has to be, this is for the finite system. Of course, in the infinite system, L does not exist anymore. It has to be reabsorbed into time or current. So I tried that, of course, and it works, but it's, yeah. So you have to reabsorb this into current and time. So one way to reabsorb space into time is to use dynamical scaling, this 3 over 2 of Deepak. So we know that time scales like L to the power 3 over 2. Okay? But then you can, but there's another scaling. We know that the current here, because of this chi variable, which I erased, the current here, we know that the current scales like t to the power minus 2 over 3 to have a finite, to have something of the same order. Yes? Here. So in fact, so that's where I'm a bit stuck. I imagine that for most, including for me, I'm not able to explain it well because I don't understand it well. But you see, it's good to see that there are things that, this is the finite size system behavior. This is the infinite system behavior. All these results are exact. But in somehow, we imagine that if we take some infinite system limit, things should match. Half of the things just match without any effort. It's just the same formula. So we have nothing to do. I don't tell you about the constants because I don't know what they are. I didn't check them out. Maybe it will not work, but we don't really care. Here, there's a factor which depends on the size of the system. In the infinite system size problem, of course, there's no size variable. But there are two ways of eliminating size with respect to time, but also there's a relation between time and current, which is implied by the fact that we want this to be of the same order of this, so chi is of the order of t minus 2/3. Okay? 5 over 2. If I use this, I get t square here. And if I use this, I get g cube here. And this matches. But of course, I can split things in a different way and get. So there's one thing which is missing, and I just hope that somebody will tell me where the missing argument is. You see, I'm not, I wanted really to try to patch everything together. I tried to do it yesterday, and of course, nick of time, and probably even if I had more time, I may not be able to do it. It's almost there between Tracy-Widom, what we learned with Satya type of behavior, or Bethe Ansatz on finite system, extraction of large deviations, analysis on this series here. Of course, all these things, there should be a crossover function. If somebody is able to do the full calculation, there should be a unique result which encompasses all the cases. But at least if we are not able to encompass all the cases in a unique calculation, there should be some matching. And as you see, it quite works, because here it works perfectly, and here it works almost, but somehow I have to make a choice. And I could, in fact, put more powers here and less powers here and get any intermediate behavior. So it just means that I'm missing one argument. I'm missing the physics somewhere. And this is an open, this is not something which is publishable. But I think this is a nice problem to think about. And probably, some of you, or many of you, will come with some argument. There must be some physical argument telling me why I have to put t square and the L 3 over 2 here, and the rest of L here, which changes the power of j using the second. Okay, so I agree that's probably not clear at all, but here it's on purpose, because I just want to tell you that this is a kind of, in my own brain, it's not clear, so I cannot explain it clearly, because I don't understand it, but it's a kind of nice thing to understand. that in the last 3 or 4 years, they have written 15 papers on the exclusion process. 15. It's not a joke. I mean, I downloaded all of them by preparing this lecture, saying that maybe I will talk about these things, but of course, I would need 1 year then to talk about all these things. But they have written 15 papers on the ASAP, because first people did the Tarzan case, then people tried to do the partially exclusion. It's much more difficult. Then you can look at the position of the first particle, or you can look at the position of the nth particle. There are plenty of variants. And of course, in this infinite system, it's not by chance that Tracy Widom are working on it, because it's their statistics is coming into the game. And for the finite system, it's another bunch of people who are working on that, using slightly different techniques, but it's other people, Derrida, Joel Lebowitz, your servitor, and many other people. And somehow we know each other, all these people, we know each other, but the techniques are quite different. And an interesting problem would be really to be able to patch. I mean, one can imagine that one day somebody will come, or a group of people, and will calculate the general function for all times and all sizes, and will contain all the information. But this is infinitely hard, of course. And we just have bits of information, and one nice thing is to try to patch these bits of information to see how they are related to one another. Okay? You had is found is that this probability, in fact, even for general M and N, is PMN. Now I erased, but just by the same type of manipulation. So let's take both of them, and then maybe I change the small m into is some normalization times an integral. Not so the normalization is from 0 to infinity. Now it's from 0 to t, where t is the time. And now you should jump. So dx1, dxn, exponential minus sum over xj's, j equal to 1 to n, plus or minus, I don't know, m minus n log xj times product of 1, the van der Monde determinant of xi minus xj square. You should now have a kind of, okay, if I call x lambda, what do you see? Let's take m equal to n. We want to study the first bond. So even the term there goes away. I can put here the log. Okay, forget about the 2's. There may be a 4 because there's a 2 here. I don't know. Maybe it's not there. I think it's too late now to correct all these things. But of course, you recognize something which looks very, 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 very much all that you have been learning with Satya during the few last days. The only difference is there is no square here. There's a positivity assumption here. Okay, but it doesn't make a big, it is different, but fortunately, this is also, how do you call it? This is a random matrix problem. So it's not the GOU, the GOL, I don't know what, the Gaussian orthogonal, it's called the Lagrange ensemble, but this is well known. And it corresponds to some Wishart, the same Wishart, of course, that Satya started with, Wishart matrices. So you start with a any matrix which is called A, which is n by n, but not necessarily anything special, not Hermitian or anything like that, and you make A dagger. So this one is Hermitian, and this is the formula for the largest eigenvalue of this type of matrices. So now you understand why Tracy Widom and everything, because it's the same problem. You just fall into exactly the same type of problems. Okay? It's just, in fact, there is a very deep connection. This I showed you by the calculation. You can show it by combinatorics. It's also a very beautiful way of showing it. It was the way it was done initially by Johansson, Beck, and Delft. So the person behind that is Johansson, early 2000s, I think. Johansson. It's a kind of classic paper. He did it by pure combinatorics, by counting Young tableaus, but he understood that the statistics of the current of the exclusion process, or the statistics of the position of a particle, which is related by this trick, is nothing but the statistic of the largest eigenvalue of a random matrix. It's the same problem. And things merge together. And there's also the Kardar-Pareti-Zhang equation, as I told you, the 6-vertex model. All these things merge together. And it ended up, as I told you this morning, that you can really, really use the formula for the largest eigenvalue of a matrix. And you can really say that the current, so Qt is given by T over 4 plus T 1/3. So T plays the role of a size here, and there is some bizarre 2 to the power 4/3 chi. Well, this is a Tracy Widom variable. So here's a connection. Okay. Here's one way to understand the connection, is to go through Bethe Ansatz, write the evolution, the green function for the evolution on an infinite space, write it in the determinant form, which is something extremely useful, extremely fruitful. In fact, Tracy Widom did their analysis not from this formula, or the equivalent formula that Satya wrote. They went to determinants. You need determinants to be able to do asymptotics. So they wrote it in the form of a determinant. And then you can connect it to the Tracy Widom. Yes, yes. And as I told you, it's this formula is really first year of university level. If you know determinants and you add lines, columns, permutation, I mean, you can really transform it as an exercise for elementary exercise in determinant calculation. No, it's a finite series. Yeah, and in fact, sometimes it's infinite. It depends on the sign. But F have very nice recursion formula. F prime m plus 1 is m fm. Fm plus 1 plus fm is f minus 1. So you have a few recursion relations which help you to add and subtract the columns and the lines of the determinant. And it's a very, if you know these few relations, there are not 20 of them, 2 or 3 of them. You just manipulate the determinant, and by brute force you end up here. Okay, this was not the original way. The original way was Johansson, some beautiful combinatorics. This is something I find absolutely, it's infinitely more beautiful than Bethe Ansatz and so on, but it's much more mathematical. It's combinatorics, and I mean, I was meant to teach the Bethe Ansatz, and it's a useful tool for solid-state physics, but it's very beautiful, and that's how he arrived to that. But there's a more elementary way. Here? Yeah, but there was an m minus n log lambda j. Yeah, so there is a product here. There's a product of the lambda j's to the power m minus n. But I took m equal to n, for example. Just as a special case. But you're right, if it's n here, there will be m minus n. But, yeah. So then, okay, all the details are important. So that's really the connection between what Satya said during this course of lectures and this Bethe Ansatz and so on. And how much time do you still leave me? Half an hour? Well, it will be enough. I want to finish with macroscopic fluctuation theory, which is very different from all that. But I want to give you a taste of that. And maybe one day you will have some advanced lecture on this thing. This is Tarzan. Let's consider another problem related. So Tracy-Widom were able to generalize it to any asymmetric exclusion process. Even though you don't have a determinant, the formulas become very complicated, but they were able to do it. I told you they wrote 15 papers on the exclusion process in the last 3-4 years. Just on, so it's, they have been very active on that. And one of your colleagues, Arvind Iyer, was a postdoc with Tracy, so he's probably very, after being a postdoc with us in Saclay, he's very knowledgeable in these things. So let's now take another problem, which is the other extreme case, which is a symmetric exclusion process. And again, I cover all the left particles, and I leave the first one empty, the right one empty. Now particles are allowed to jump backwards and forward. And you can ask the same question: what is the generating function of the cumulants of this current? So it will be quite different from the totally asymmetric case, or even partially, because this is symmetric. In the long time limit, that's why I wanted to show you that, it's not in t, but in square root of t. Okay? And there's a function here which we call e of lambda. Let's call it f. And it's a function of lambda, but not a function quite of lambda. It's a function of omega, where omega is exponential lambda minus 1. Okay? And the function f of omega is very pretty. So it's very pretty function, not unrelated to all that we have seen. There is an explicit formula for this function. 1 over square root of pi, sum n bigger or equal than 1 minus 1 to the power n minus 1, omega n over n 3 over 2, I think. So you see it's and you can find an easy analytical continuation of this formula, because this is only valid for omega close to 1, less than 1, sorry, close to 0. But there's a very trivial way of continuing it, very simple. You just expand the log and get it. It's an art of finding analytical continuation, but here it's simple. Just expand the log with respect to omega and compute the decay integral, and you'll get the same thing. It's a very good formula. And again, we can compute the cumulants. So we can compute the average current. There will be an average current, although it's symmetric, because of course there is diffusion. So the average current is in square root of time. It's t over square root of pi. The variance has a nice formula also, and so on and so on. Qt. Sorry, I have this very bad habit of going from upper cases to lower cases without realizing it. T over square root of pi. You can go to the third cumulant, still t over square root of pi multiplied by some number with square root of 3 and so on. And you can find the large deviation function has some exponential minus square root of t, g of q, and so on, which behaves like q cube for large q, and so on and so on. All this very nice work was done by Derrida again, and his student at that time, Antoine Gershenfeld. Okay. Again, using Bethe Ansatz, it's a very beautiful paper, and they were even able to generalize it further if you have a finite density here, and so on and so on. Okay. So there is one question we don't know how to do and we are trying to solve. Is the question of, this is the question of the current. Now suppose I mark a particle somewhere and I call it a tracer, and I want to know the same problem. I call xt the position of the tracer at time t. We don't know how to do the same calculations. And again, all this is quite technical and relies on Bethe Ansatz. On the infinite line, Bethe Ansatz for the symmetric case, the expressions are much more complicated. You don't have determinants, but they somehow pop out through the calculations, and so on and so on. But now I want to conclude this series of lectures by somehow trying to kill everything that I said and going totally backwards. You can tell me, okay, I mean, this is very nice. I mean, all these problems, it's very technical and Bethe Ansatz, and it's heavy. Each problem to solve takes weeks or months. People who are playing with that are, most of them, I'm not talking about me, of course, but most of them super smart people, and it's just horrible. I'm a physicist. I want to find a physics way to deal with these things. I mean, you're talking to me, you try to sell me all your things with a kind of stupid model of a pipe between two reservoirs. And I agree with you, it's a very, you're talking to me. It's a very physical model. I want to understand that. Physics has to understand that. No Boltzmann weight. But do I really have to study all that? I mean, to do all this arcane mathematics, okay, beautiful. But you probably had to be a bit pervert to love these kind of things. And no, I mean, there should be another way. Okay, so yes and no. So this is going to be the last few, maybe not minutes, but 10 or 15 minutes of these lectures, opening to further learning from you, if you wish so. There is now a way people think to try to understand this kind of problem without having to do all that. Physicist. I like physics. I want to understand things in a physical way. So what do I have? Well, I have a pipe between two reservoirs at different densities. It's a very large pipe. I don't care about exclusion, not exclusion, whatever it is. I just want to describe that. So how are you going to describe that? Something of length L. You have a current. You may have some field, which scales like 1 over L, a weak field, which goes 2L maybe, which pushes a particle if they are charged, and you want to understand that. Okay, how will you describe that physically? Well, you have a local density rho of x and t in the pipe. You have local current, small j, big J, I don't know, g of x and t. In the simple model, particles are not destroyed or not created in the bulk. So you write conservation equation. It's one dimension. Otherwise, you would put a divergence. I mean, you're a physicist. You don't need to do, we don't need to do arcane mathematics to write that. Now, what is the current now? Well, the current is minus gradient of the potential, minus gradient of the density, has to be, with some diffusion constant, which may depend on local density if it's a kind of nonlinear material, complicated material. So you see, I'm just really I'm trying hard. It's hard for me to do physics, okay? And so this is the current due to local density gradient. And there is also the current due to the field, okay? And the current which is due to the field is just the field, which is nu. The 1 over L will scale out. It's intended to scale out. This you can do by yourself. It's very easy. Multiply by some diffusion constant. sorry, susceptibility, response, susceptibility, conductivity. I mean, really, this you really don't need to learn Bethe Ansatz. This is the beauty of physics somehow, if you want. It's just common sense physics. I write a diffusion equation or conservation equation, and I write a constitutive equation for the current. And the current, I know it has two origins, gradient density, density gradient, plus field. And what is the response to a field? This is the field. The response to a field is conductivity. This is basic. Okay, so I just plug it in. Just plug it in with the minus signs. I put back the gradient and so on, just to be fancy, in any dimension, minus nu gradient of sigma of. The only thing I need to know is this local density, local diffusion constant, and local response coefficient. Okay, so this thing, for example, is quite difficult to prove. The proof of this mathematical proof, physical proof is trivial, there's no proof. But the mathematical proof was again done by Varadan and so on, and his collaborators. Also Lebovitz, Spohn, Anna De Masi, Presutti, in the 80s and early 90s, I think, for the exclusion process. For the exclusion process, because this is the exclusion process is the toy we try to understand things with. It tells you that d is equal to 1, and sigma is just, there's a stupid factor 2. It's a question of normalization, but it's again rho 1 minus rho. Because we know that the current is P minus Q, rho 1 minus rho, and P minus Q is the local intensity of the field. Okay, this is very nice. If you solve it with some initial condition, with boundary condition, you will find a density profile. But this is not what we want to do. As you remember, what we want to do is something more elaborate. What we want to do, and this is what I told you 2 or 3 days before, I can't find my notes anymore, this will give you the average profile. I don't know what it looks like. It depends on if d is constant, and even if we take sigma to be constant, or it would be a linear profile. It can be a curved profile if it's more complicated. If nu equal to 0, it's a linear profile. But we want something more complicated. Remember, we want the probability of seeing any profile at time t and any current at time t. And this, I try to convince you that there is a large deviation functional of the current and the density. And I try to convince you that this large deviation functional is the important object, which allows you not only to calculate the average profile, this is for the average profile, but also fluctuations and even large excursions very far away from this average shape. This would, as I tried to convince you, if you remember well, in the case of an equilibrium gas, forgetting about the current, this was the free energy. This was the integral of free energy, rho t minus phi, rho bar f, rho bar t. So I really try to sell you the fact that this is a free energy analog of for non-equilibrium systems. And as I told you, Lebovitz, Beer, and Derrida computed that for the exclusion process, for example. But we want a general scheme without having to use matrix ansatz, Bethe ansatz, any ansatz. We want to find a physical way to calculate that function, that rate function. Let's call it I, not to overemphasize the analogy with free energy. I want to compute this I. Okay. Okay, so this is what people have been working on in the last 10 years, or slightly more, and which it's not done yet, but a very substantial progress has been made by the Rome school, many people, but you can say that the fatherly figure, the leader, I don't know, this is always complicated. But yeah, you can say that Giornalasigno. It's Giovanni Giornalasigno, elderly person, around I think 80 years old, together with a whole team of mathematicians, Bertini, I will forget the names, Landim, and there are others, Gabrielli, De Sole, and so on and so on. It really began as a very abstract mathematical tool, but it can be recasted in much simpler physical language. The idea is to rely upon local equilibrium, and finally, once you know the result, it always looks simple, but it was really a long route and difficult route to reach there, and they proved it. So it's not only hand waving. They showed that this picture can be extended. This is an average picture. We want to have a fluctuating picture. We want to have rho which can have excursions beyond its average value. Well, this picture can be extended by just adding a Gaussian noise term to this current. So there is a Gaussian noise contribution with an amplitude which is given by the same susceptibility which is here. Okay? So now your equation here, it would have a, let's not write it completely, but it would have a stochastic. You all learned about Langevin equations. So it will be a Langevin PDE with gradients and so on. It will be a kind of Langevin heat equation, nonlinear heat equation. It's mathematically a complicated object, but physicists have been playing with that for a long time, for percolation, for, I don't know, there are many models in even in statistical physics where we have noise, Cardar-Paris-Isang if you wish. And the nice thing is that the noise here, it's a white noise with a vanishingly small amplitude, which vanishes inversely with the size of the system. So it's a weak noise. It means a weak noise, that fluctuations are small. You're close to the classical limit, if you wish, or you're close to the saddle point. L is very big. There would be a saddle point calculation to do. Okay? And now, the thing is, I can put it back here, in fact, square root of sigma. The thing is that this is a Langevin equation. Okay? It's kind of complicated, but it's a Langevin equation. So you can write, I plan to do it, but I think I will not do it now. It's a few minutes. I prepared it. It's not very long, but I think you know enough now to believe me. You can write the probability of rho at time t as a path integral. Do you agree with that? You can write a path integral. It's not very difficult. If you wish, okay, I can come back to this later. But you can write, because you know the weight of the Gaussian noise, so you can write the probability of having rho xt gxt knowing rho at time 0 and g at time 0, you can write it as a path integral. So the problem with path integrals is that they're always very long to write. But let's write them. So a path integral over all d rho's, all dj's, of course, all which started with rho 0 at time 0 and end at So this may look really daunting, but it's in fact amazingly easy to derive, much more easy than most of the things we have done here. So of course you have the compatibility condition which comes from the conservation, and you have a weight. So this is a kind of, if you wish, there is some technicality here, but it's a kind of black box. It's automatic. I give you a Langevin equation with a white noise. There is a path integral. If you don't know how to do it, go and see and ask somebody who knows to do it, and he'll do it for you. She'll do it for you. So, or you learn to do it and you do it. But there's nothing. The crucial point was to write the equation correctly. From here to here, it's purely technical. And although it's very heavy and so on, it's much easier than what it looks. It's just heavy to write. Okay, I've rescaled the size of the system to 1. And then you end up with something like that, which is quite natural. I can just tell you in 1 second where it comes from without doing it. In fact, even if you don't know how to do it, you can write the result without knowing how to do it. But of course, it's better to be careful and so on. Okay? How do you get that? It's in fact very simple. I told you the noise is like that. So it means that the weight of the noise is something like that. Because it's a space-time noise, you have to write path integrals. It's L psi square. Okay? With an integral. Because you have, if you just discretize psi I tau, you will have all of them here, sum, and so on. Now psi, just eliminate it from this equation. Again, sorry, my capital and uppercase and lowercase letters are the same. Huh? So if you just eliminate it from this equation and put it back into psi square, you just get that. You really don't need to do anything. Of course, if you want to learn how to do it properly, you have to go through some field theory, very little. Otherwise, it's just trivial. You agree? You have a Gaussian measure for the noise. You know how to express the noise in function of the current and the density. You put it back. But the nice thing is that here L is big. So you can do saddle point. I'm almost ending. And the saddle point, don't forget that we are looking at some kind of large deviations. So we are looking at a function of this type. Well, it just tells you that I of rho and g, which is my large deviation functional, is just given by the max or the min, there is a minus sign, of this number, of this integral. Because saddle point tells me that I have to take the min of that, there is a minus, okay? And it means just by identifying that this is given by the value of the saddle. That's what Satya has been doing, taking the saddle value. So it just gives you a formula for the large deviation function, functional. It tells you it's the mean. Let's remove everything. Just the mean of that. Over rho and g. Satisfying the relation at rho d rho dt, of course I have to keep conservation. So I just have to, and now you should, okay, of course I have to remove the exponential and everything. So you see, this is a huge progress, although it looks very naive and so on, but I told you at the beginning, we don't know how to generalize entropy, free energy, and so on to non-equilibrium processes. Then I told you that we think that the right generalization are made by these large deviation functions. But I told you we don't have a general scheme to compute them. We don't know. We can express them as mathematical functions, probability of la 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 la. Then how do we compute them? And then, okay, we try to compute them by using sophisticated techniques, either random matrix techniques in the case of random matrix eigenvalues, that's what Satya told you, or Bethe Ansatz techniques in the case of the exclusion process, and we got some precise, fine results on some very precise models. The advantage of that, so of course I didn't tell you, this is not true for all possible models. It has to be diffusive, it has to be weakly asymmetric. For example, the Tarzan does not fall into that game because the Tarzan corresponds to nu going to infinity. There are plenty of things that I've put into the carpet, but globally now, for driven interacting diffusive systems, there is a kind of global scheme, and the only thing which I have to know from microscopic dynamics, just like in hydrodynamics, where I have to put by hand the value of viscosity, of heat conductivity, and so on, I have to know or to calculate from microscopic dynamics the value of the diffusion constant and of the susceptibility, the conductivity. And then for a large class of interacting systems, I have an expression for the large deviation function. Okay, now I have to minimize a functional, but you know how to do that. Lagrange equations. Of course, this becomes a purely classical problem. I have a Lagrangian, okay, it's a bit ugly, but why not? And I just apply Euler-Lagrange, this you learned. So ddl, ddt, ddl over q dot is equal to dl dt, or I do variational calculus, and I get equations. I don't know if I write them for you, but by the way, if I'm interested only in the density and not in the current, I have to minimize that over rho and j, and then optimize over j. So I have a double minimal procedure. If I'm interested only in j and not in rho, okay, so this contains too much information. I can contract it, that's the technical word, as if I have a function of two variables, I can integrate one. So I will get the large deviation for the current, large deviation for the density profile if I want only one of them. So now I can use Euler-Lagrange variational method, and I'll get some equations for the so-called optimal profiles. I will find rho star, again, same notation. There's a great unity in physics. That's what is beautiful. Of course, Satya and myself, it looks very similar because we work in similar subjects and we work in similar places, just a few minutes apart, and we know each other. But even if you take people from further fields, in fact, there's plenty of similarities with what Sumit told us. So it's full of similarities. So we will find the optimal rho and optimal j. But okay, I mean, this I really don't have the time. I'm finishing in a few minutes. It's really the very end. There are some transformation of variables and so on. The nice thing is that you can go to optimal p and q, which are variables which are made from these ones. I'm really not entering and you will find equation like that. Q dot for the optimal, q is really rho, it's star, but p is something different. It's a conjugate variable. The nice thing is that in fact it's a Hamiltonian system. It's a Hamiltonian structure. Okay, so these are probably the last equations or so that I'm going to write. You will find some nice system of coupled equations, which again, the only microscopic information that you need to write these equations are just the diffusion constant and the sigma, the susceptibility. So they look like they are coupled. There is a Hamiltonian, so they are really Hamiltonian equations. I mean, there is a Hamiltonian such that q dot is dh, I'm not writing it, dp, and p dot is minus dh dq. It's a Hamilton density. So it's a field, it's a classical field theory with momentum and position. But as you can see, these equations, they are complicated. They are nonlinear. They are second order, nonlinear, coupled. One thing which is quite horrible, especially for mathematicians, but not so much for physicists, is the minus sign here. You know, if you put a minus sign in front of a diffusion equation, it has a tendency to collapse. And you know, you can have a singularity. If you diffuse from a delta function, it will become a Gaussian. But if you anti-diffuse from a Gaussian, it will have a boom, a singularity in a finite time. So these are stiff equations. I didn't tell you about boundary conditions. They are quite complicated. But I am not the only one. Let's think about it. It's quite an exciting time, in fact, for physics, at least statistical physics, because we have now a scheme for understanding not all, but a large class of systems out of equilibrium, a very large class, and we have new equations. And in fact, these equations, they are not ugly. They are very symmetric. I mean, you see, they are quite nice. And it's not every day that we have a new set of equations, quite generic, which can be applied to various problems. You know, it's just like having a new set of Navier-Stokes type of equations. It's not Navier-Stokes equations have given work to people for 200 years at least, and it's not over. As you know, turbulence is one of the major open problems in physics and applied mathematics. So I don't say that these equations, I don't know yet, nobody knows if they're as important as the Navier-Stokes equations, but at least they allow you to describe systems far from equilibrium. Okay? I can take rho 1 and rho 2 as much different as I wish. There are some underpinning hypotheses. They're not totally general, but they are far enough general. Okay? So now there's more and more people, for the moment being quite a few, but it's growing, people who are trying to study these equations, to develop numerical methods, because they are stiff, because of this minus sign, to develop numerical schemes to try to get solutions. For example, one of my colleagues and friends, Yariv Kafri, in Israel, is working on that. Also the Kurchan group in Paris and other people. Some people are trying to develop some approximative scheme, you know, like they look a bit like Schrödinger or heat equations. So you can think about WKB methods, things like that. There is a small parameter hidden somewhere, because as you remember, there was a mu everywhere that has here gone a bit astray, but it's still there. It's hidden in the boundary conditions. So there is a small parameter. So you can do perturbative expansion. You can try to measure some consequences of these equations. So it's a new field. It's quite exciting. Okay? The problem is, and that's where I'm just wrapping around and finishing. The problem is that even if this is a very general framework, nobody knows of any non-trivial solution of these equations. What I mean is, nobody knows, for example, in the case of the cases I've shown to you, AZEP, this Derrida-Gershenfeld thing, and so on. Nobody, we can write the equations. So then what I said 15, 20 minutes ago, then we could get rid of Bethe Ansatz, random matrix, matrix Ansatz, whatever you wish, and just solve these equations. The problem is that nobody knows how to do it. We can write the equations, but we cannot extract beyond some non-interacting case, which amounts to taking sigma linear. Then you see they will decouple. If sigma q is q, this is 1, they will decouple if you do and d equal to 1. So you can solve in p, in fact, by putting p is equal to exponential something, it will become linear. You solve in p, you can solve in q. But beyond the case where the particles do not interact, we just don't know how to solve them. And precisely what has happened up to now is that to test this theory, to see if it's correct, what's the only way? Is to test it against exactly solvable models. Because we don't have any way of solving these equations exactly or directly. What has been done is precisely what I have been telling you about in the last 6-7 hours, is that using Bethe Ansatz, matrix Ansatz, so we are back to it. Many people have been able to derive exact formulas for large deviation functions, for profile densities, for current things, current fluctuations. And then, using these formulas, you can plug the result into the equations and check that it works. You see? So it's quite strange. We have equations, we don't know how to solve them. On the other hand, there is one simple model, one and some other ones which are similar to it, on which we have very elaborate techniques, arcane techniques. I agree with you, dry and complicated techniques. But by using these techniques, we can beat these models to death, almost, and get some formulas. And the beautiful thing is that then these formulas, we can check that they fit into this framework. But we are not able, none of the results, I think, that I've told you, maybe one at most, but still, none of them can people extract it directly from these equations. Okay? For example, and this will be really the last few words, I think some of you will probably work in a related field. Recently, with my postdoc nowadays, whom you probably know, some of you, Tridip Sadhu, we have been trying to understand, using macroscopic fluctuation theory, using these equations, the problem of tracer diffusion in this symmetric exclusion process, which we cannot do either by Bethe Ansatz. So this is a simple problem. You have particles on a line, infinite line, put them everywhere with a finite density rho, let's say 1/2 density. You look at one particle which was at 0 at time 0. You take the exclusion, simple symmetric exclusion process. You know that the position of the tracer on average will be 0, on square average will be square root of t divided by p, 1 minus rho over rho, blah, blah, blah. But we don't know of any higher moments. We don't know how to compute the probability distribution function in the case of the symmetric exclusion process. We don't know how to calculate the large deviation function. And the hope is to try to extract information from these equations, or to be able to generalize the Bethe Ansatz solution to get it, and then to plug it here and to see if it works. This is precisely what we are trying to do. So I think I will end here. So look at, these equations are quite nice. So they are called the macroscopic, this is called the macroscopic, I don't know if I said the name, macroscopic fluctuation theory. And if you look on the web, you will see more and more papers on this subject. But for the moment being, this has not killed, far from it, the subject of solving exactly models, because when you have an exact solution, it gives you something that you're sure about and on which you can test other theories, you can test approximations, and you can check things. And as I told you, for example, this theory has not been generalized in the case of, in fact, it's only valid in the case of weakly asymmetry. 1 plus epsilon, 1 minus epsilon for the jumps. But if I take P and Q equal to 3/4, 1/4, and even worse, P equal to 1 and Q equal to 0, we don't have this theory yet. One day somebody maybe will be able to write similar equations in the case nu going to infinity. By the way, here I wrote the equations for nu equal to 0, I think. Yeah, these are the nu equal to 0 equations. There's another term otherwise. So, okay, I hope you will be able to do some progress in this field or some other fields. And thank you very much.